Welcome to AP Podcast 16.1. If you're wondering what's going on, we're just finishing Chapter 6. You're in the right place. Chapter 6 and 16 combined to make our whole thermodynamic unit. So don't worry, you're in the right spot. Now, we've got a new term. This little podcast is on spontaneity and entropy, and you'll notice the word entropy sounds a lot like enthalpy, which unfortunately caused some people to have some issues. Sometimes they mix them up a little bit. So we're going to try and keep them straightened out, but basically what entropy is, at least for our purposes, is how much disorder there is in a system. It's a factor on why some reactions will go completely on their own, spontaneously. For example, imagine a car sitting in a field. Come back 20 years later, it's all rusted. Put some salt in some water. It dissolves all on its own. If the temperature is below zero, you put some water on a sidewalk, it turns to ice. If there's some gas let out in a room, it's a matter of time before that gas takes up all the space in the room. Those things are happening all on their own. What's that factor? Well, that factor is entropy. All right? And I've got a couple blurbs here, and you're going to see a word you haven't seen yet. We're not going to deal with it right now, but we're doing thermodynamics right now, and that has to deal with the initial and final state of a reaction and all the energy involved. Okay? But to really describe a reaction, you also need to know the kinetics that is involved. And the kinetics is really how fast a reaction goes. So something that's, if you're reading our text, you're going to see that mentioned a few times. Okay, so here we are again with the first law of thermodynamics, and that energy and the universe cannot be created or destroyed. And keeping track of this stuff doesn't allow us to correctly predict whether a reaction is going to go or not, and that's why we really need entropy to help us with that. So what exactly is entropy? Well, let's see. Oh, I'm waiting for a slide to go. There we go. So entropy is this driving force that allows for an increase of disorder in the universe. If you think about most things just laying around, they're going to break down on their own. Things don't get built up in the universe. Things break down in the universe. Things get more disordered in the universe. Think about your room. You get it all cleaned up, and then just almost magically, you come back a week later, and it's a complete disaster. How did that happen? It's almost magical. That's spontaneity, right? Now, not necessarily chemical spontaneity, but at least you can kind of get the idea. It's what's the most likely arrangement that's going to happen. If I were to walk into your room, would it be super clean or would it be a pit? So you've got the idea. It's the most likely possibility. If we think about a very simple example of, I've got this this ball and I've got 4 gas molecules, right? Now the probability of me finding any one gas molecule is pretty much the same. They're not all going to be bunched in one little area over here. They're going to be spread out. They're going to be random. And that's kind of what we're looking at. Your book does a really nice job with a bunch of different diagrams, but just in order to keep our time straightened out, we're not going to go over it. So I want you to think about this. If you think about enthalpy, it would seem like things that are going to give off energy would be spontaneous. They would just go on their own because they're coming to a more grounded state. Therefore, it's more favorable to run forward. Right? But if you look at this reaction right here, ammonia and oxygen going to NO and H2O, that gives off a lot of energy. I mean, look how much energy is given off on that. 909 kilojoules per mole, right? But you put ammonia in oxygen, just imagine having some ammonia in air. This little product right here does not happen all on its own. You don't make NO gas and water. It just doesn't happen. And conversely, you would think that reactions that require energy to go would not be spontaneous. They wouldn't happen on their own because you got to add energy to get them to go. But if you think about an ionic compound, and the one I've got right here is KCl, but that could easily just be NaCl. You put that in water, and then it just breaks up into ions of potassium and ions of chloride. And you can see that it takes energy to do that. So those things are happening in spite of the enthalpy change. And so what's going on here? Something is getting it to go, and the key there is this other factor, entropy, right? And there are some really good, if you want to go to the Khan Academy, he does an amazing job on this, a real good job on this. But anyways, that's what we're looking at right now. Okay, so we're going to look at entropy a couple of different ways, but one of the ways we're going to look at it is positional entropy. And when we're talking about this, we're talking about the molecules or atoms in their, I guess, in their physical position. Okay, look at this first statement. A gas expands in a volume because the expanded state has a higher positional probability of states between the system. Okay, so what we're saying is if you have a solid, now think about how atoms are in a solid. They're locked in some kind of nice little tight crystal, right? If I could draw a nice cube, I would. Okay, and so that's pretty ordered, right? Now you get to a liquid, liquids are flowing, and the molecules are flowing past one another. That is more disordered. And then you think about a gas. Gases, boy, they're just spread out and randomly flowing wherever. That's even more disordered. So as far as entropy, solids are the most ordered, liquids are less ordered, and then gases are the least ordered. And so if you want to think about how would I find that change in entropy, the delta S, look at that. It's the S final minus the S initial, and we can do that simply with the charts that we have. So let's go ahead and look at the next thing. Okay, so for each of the following pairs, choose a substance with a higher positional entropy at a given temperature. So pause the video at this point, take a guess on these, and see if you get what I get. Alright, did you do that? Here we go. We've got solid carbon dioxide or gaseous carbon dioxide. Well, which one has the greater disorder? Well, hopefully you said the gaseous, right? Its entropy is higher. Nitrogen gas at 1 atmosphere or nitrogen gas at 1/100th of an atmosphere. Which one's going to have more positional entropy? This one. Okay. Why is it not this one? Well, think about this. If you have a pressure of 1 atmosphere, that's going to cause the particles to be squished closer together. Gas at less pressure has a greater chance of spreading out, right? Now, here we go. Here's the sign of the entropy change for each of the following. The sign, okay? So solid sugar is added to water to form a solution, right? What's going on? Are we getting positive or negative? Alright, so for this situation, the sign is going to be positive because we're talking about a solution versus a solid. Way more positions for that solution to be in than a solid. What about this one? We've got vapor, which is a gas, right, going to crystals. Yeah, that's going to give us a negative value. There were much fewer positions for this S value than there are for this S value. All right. So how can we kind of make sure this really works? Well, let's think about this. Okay, we can find the delta S by subtracting the values of the entropy that we get from that chart. Now, last chapter when we were doing the heats of formation, I said, hey, there's some S values there. You need to look at that. Well, just like before, it's just the entropy for the reaction is simply the products minus the reactants. So let's look at this. Here are some values. Now we've got this reaction. Nitrogen plus hydrogen gives you ammonia, right? Now if we do the sum of the products minus the sum of the reactants, we should get a value. So 2 times that, 193, and those values are given up here. And then we've got just 192 for this is for nitrogen, right? This is for hydrogen. And then this value right here was for ammonia. Okay. When you work it out, you get negative 199 joules per Kelvin. Now, does that make sense? Well, let's look at this. If we were to think of what we had 1 mole of stuff and 3 moles of stuff combining to make 2 moles of stuff. Does that make sense? That we should have a negative S value? Is this not more ordered, those 2 moles, than those 4 moles of things? So that's really kind of what we're looking at. So hopefully you could see from that reaction that this reaction is getting more ordered, and therefore the value for S should be negative. Okay? Kind of confusing stuff, I know, but we'll talk about it and spend a lot of time with it in class. Again, if you have questions, let me know. See you next time.